So far in this class, we've explored lots of links between electricity and magnetism, and today we're really going to sort of put the icing on the cake, so to speak. But before we do that, let's review what the links between electricity and magnetism that we've seen are. It's not really basically what I'm going to do is I'm going to review essentially the whole course, actually. I'm going to do a little bit more than just exploring the links between electricity and magnetism. I'm going to talk about everything that we've done so far. And if you recall at the beginning, we started with the basic statement that electric charges, create electric fields. And this was sort of neatly summarized in Gauss's law, which says that the electric flux through a closed surface is equal to the charge enclosed by that surface divided by epsilon 0. Right, so this was the electric flux through a closed surface. Basically what that means is that in order to get an electric field, in order to create an electric field, there must be some charges present. Okay, so that's not even a link between electricity and magnetism. That's just sort of the first statement. Then when we turned our ear to magnetism, one of the first things we observed is that there's no such thing as a magnetic monopole. Right? Another way of actually writing this expression, to say that there are no magnetic monopoles, that's the same as saying that the magnetic flux through a closed surface is equal to 0. Essentially what that tells us is that there's no such thing as a magnetic charge like there is an electric charge. Since there are no magnetic charges, there can be no magnetic flux through a closed surface, right? So we've seen both of these ideas before. So charges create electric fields, but there are no magnetic charges to create magnetic fields. To get magnetic fields, you need something else. And that brings us to connection number 3, which is to say that currents. So what does create a magnetic field? Well, an example. Currents create magnetic fields. And just as an example, we saw that the magnetic field, for example, due to a wire, was mu0 times I over 2 pi r, right? So we certainly have seen, and that's just an example, right? There are many different ways that current distributions can create magnetic fields, and we've already talked about that. So this was the famous connection that Ørsted made in the early 1800s that forever linked electrical phenomena with magnetic phenomena. And then the last one that we saw when we were talking about electromagnetic induction was Faraday's law, which tells us that a changing electric flux, a changing magnetic flux induces a current, but of course in order to have a current, you must have some sort of electric field that's pushing charges around. So effectively what we're doing by changing the magnetic flux, we're creating an electric field. We didn't talk about that too much in detail mathematically or anything, but that's in effect what's happening. If a magnetic flux is changing in time, then that creates an electric field, which then will drive these EMFs and these currents and those things. Okay? So far, this is kind of a summary of everything that we've done in this course. But there's one sort of missing piece. And in many ways, you can think of James Clerk Maxwell, who's a Scottish physicist. He lived in the sort of the mid-1800s. He was one of the first people to notice this, that there was actually something missing from this list, something sort of important missing from this list. And so he proposed, just by pure symmetry, right? He proposed that, well, if a changing magnetic flux creates an electric field, perhaps a changing electric flux can create a magnetic field, right? By the way, I should clarify here, I'm sitting here throwing around these flux symbols. Both of these fluxes that I'm indicating in 1 and 2 are fluxes through a closed surface. This flux right here would be through through an open surface, or really through a closed loop. And that's different, and you guys have seen why that's different, right? So you can only induce these EMFs, for example, around a closed loop, like if you have a wire and you've got a magnetic field that's changing in strength inside that wire, then you can induce an EMF, consequently an electric field. But that closed loop is different than these closed surfaces that I'm mentioning here. So let me summarize this missing ingredient up here. So this was Maxwell's proposal. This turned out to be true. And if you think about it, this really should be filed under statement number 3 that I had up on the board earlier. Statement number 3 being the answer to the question, what creates a magnetic field? Well, it turns out you add this to that list, right? Not only can currents create a magnetic field, but it turns out also that magnetic or electric fluxes that are changing in time through a closed loop can also create magnetic fields. So it's another source of a magnetic field. So with that in mind, those 4 statements can sort of be neatly summarized into a set of 4 equations that we sometimes call Maxwell's equations. Now we're not going to study those equations in any kind of mathematical detail. This is not the appropriate venue for that. We would need calculus, and that would take some time to do justice. The math is beautiful, by the way. If you ever get into a more advanced study of physics, then it's really not to be missed. It's a great thing to see. But these equations, this theory that Maxwell proposed in these 4 equations, really sort of ties together and summarizes all of the possible connections between electricity and magnetism, and really forms the foundation of all of this classical electromagnetic theory. So it really can't be overstated, the importance of noticing this symmetry here. Now, like I said, we're not going to get too deep into the math, but there's one remarkable consequence of Maxwell's proposal, and that is it predicts the existence of something new, something called an electromagnetic wave. So what is an electromagnetic wave, and what does this have to do with what I just said? Well, it turns out that something very interesting happens if I take an electric charge, say, and I wiggle it, say, up and down, okay? And to show you what happens, let's look at a simpler scenario first. Let's look at a charge at rest and the electric field that it creates. Okay, so here's my electric charge. Let's say it's just positive for the sake of argument. You guys know what type of electric field this thing is going to create. It's just going to point radially away in all directions. Okay, so this is what happens if I have just a positive charge just sitting there. Now let's take this charge and let's push it in the positive y direction. Let's push it up. What's going to happen? Well, if the charge was originally right here, then at some later time it will have made it up here. And you may think that the electric field lines would just travel right along with the charge. But if you actually if you sort of look more deeply into Maxwell's equations, you find that that's not actually what happens, right? In fact, it takes a little while for the field lines to catch up with the charge. And so how does this work? Well, out beyond some certain distance, indicated by this dotted line here, the electric field will look the same as it did originally, because out here, you're not going to be able to tell that the charge has moved yet. If you get really close to the charge, then the electric field lines follow along pretty closely. And so to find out what's going on inside this blue circle here, what I really need to do is try to sort of smoothly connect these electric field lines. And you can see that I'm going to get these sort of interesting looking shapes. This one's going to be straight down. This one's going to be straight up, but the rest of them are going to have this funny shape about them. You see, you're going to get some sort of distortion of these straight line fields. In fact, you're going to get these wiggles. And what's going to happen, over time, these wiggles are going to propagate outwards, such that if you wait long enough, all of the electric field lines would have moved up here, and it's going to look like this again, right? But just a little bit higher up. The point is that the electric field lines don't move instantaneously. They have to sort of go up, and they sort of, in doing that, they kind of, these electric field bumps, these wiggles, propagate outwards, right? Now, how fast do they propagate outwards? Well, to answer that question, we need to actually apply Maxwell's equations, which we're not equipped to do here. But, I mean, think about what's going on when as this is happening, right? The physics is pretty wild to think about, right? Because as I move it from here to here, right here in this region, I have a changing electric field. Consequently, I have a changing electric flux through any closed surface or any closed loop that I choose to draw. If I have a changing electric field, that's going to create a magnetic field, according to Maxwell's new proposal. But if I have a changing magnetic field, that means I have a changing magnetic flux, and I'm creating an electric field, right? But then if I'm creating an electric field, I'm creating a magnetic field. So I have this mind-bending intermixing of electric fields and magnetic fields, one building the other building the one, sort of going through this dance, propagating outward at some speed off to infinity. It really is a sort of a mind-bending and crazy thing to think about. I'll spare you the math, like I said, but it turns out that you can calculate the speed at which this little wiggle propagates. If you apply Maxwell's equations rigorously, you find that that speed works out to be 1 over the square root of epsilon 0 mu 0, where epsilon 0 and mu 0 are the constants that we all know and love, the permittivity of free space and the permeability of free space. Remember that epsilon 0 is a static quantity related to electric fields. Mu 0 is a static quantity related to magnetic fields, right? But they both show up in this formula for V. Take a second, pause the video, take a second and calculate what you get when you plug in these numbers. So pause and do that. Okay? When you plug in those numbers, you should have gotten this right here. You should have gotten something that was about 2.99 or 3.00 if you round it times 10 to the 8th meters per second, which, as many of you know, is what we call the speed of light. This is unbelievable, right? What we have just seen is that with this particular combination of static quantities, we get the speed of light, which had been known for a long time. Since the 1600s, we had known what the speed of light was. That was discovered by a Danish astronomer in the mid-1600s by looking at the moons of Jupiter. And so we knew that light traveled with a speed c, but we had no idea that it had anything to do with electric fields and magnetic fields. And this sort of proves, or at least it strongly urges us to believe, that electric and magnetic fields are really what light itself is made up of, right? This was a huge victory for Maxwell. It predicts that light itself is an electromagnetic phenomenon. Let's talk about what I'm going to call an electromagnetic plane wave. And I'll explain what I mean by that. Okay, so I'm going to draw myself a set of axes. Let's call this our x-axis, this is our y-axis, and this is our z-axis. Let's imagine that I have my charge sitting on the z-axis and I sort of have it oscillating up and down in time like that. You know what that's going to do? That's going to create these ripples in the electric field that are then going to propagate outward, say in the positive y direction. So let's say at some moment in time, at the origin here, I have an electric field that points up, and it has some magnitude that I'll call E max. Okay, so this is my electric field vector at the origin at some point in time, at some moment in time. A little bit to the right, the electric field is going to be not quite as big, and if I look here, it may be like that. So I'm just looking at how the electric field vector looks at various points along the y-axis. And I might get something like this. If I draw sort of an envelope, you can see what this looks like. It looks like a wave, right? The distance from one peak to the next peak is called the wavelength. And according to Maxwell's equation, if I set this up, this electromagnetic ripple, this disturbance, will then propagate outward with some speed c, which, as you know from waves, is equal to lambda times f, right? Because the speed of the wave is always equal to the wavelength times the frequency. So this is what the electric field looks like along the zy plane. Turns out the magnetic field looks similar, although it's not going to point. It's not going to point in the positive or negative z direction as the electric field does. It's going to point in the positive or negative x direction. So this, at the origin right here, I would have some B max, the maximum value of the magnetic field. At a point right here, it would be a little bit weaker, kind of like the electric field is. Here, the magnetic field would be 0. Here it would be a little bit bigger. B max again. Here. And then B max again. And so if I draw my envelope for the magnetic field, it looks something like that. You can see that the electric field exists in the zy plane, whereas the magnetic field exists in the xy plane, right? But wherever there's a maximum in the electric field, there's a maximum in the magnetic field. Wherever the electric field is 0 along the y-axis, the magnetic field is equal to 0 too. So this is a picture of what I call an electromagnetic plane wave. Now, would I really get this type of electromagnetic wave if I were to wiggle a charge up and down along the z-axis? Probably not, but this is actually a solution to Maxwell's equations, and it works, and it really is the simplest model of an electromagnetic wave that we can think of. And so this is the first thing that I want us to look at. Let's look at some other general properties of this electromagnetic wave, right? So I'll make a list over here. By the way, the reason we call it a plane wave is because let's say that this, at the origin, for example, the electric field has some magnitude, I don't know, 100 newtons per coulomb or something like that. It means that at every single point in the zx plane at y equals 0, every single point in this plane has the same value for the electric field and the same value for the magnetic field. And these planes then propagate to the right here with out at the speed of light. So again, to highlight some of these properties, you'll notice that E, the electric field, is perpendicular to the direction of propagation here, right? E is perpendicular to V, B is perpendicular to V, and E is perpendicular to B. They're all three of these things are perpendicular, right? So how can we make sense of the relative directions between these things? Well, you have to use a new right-hand rule, one that I call right-hand rule number 4. And the way you do this, the way you sort of can see how this works, is for right-hand rule number 4, you put your fingers in the direction of the electric field. Let's say I'm doing this at the origin. I'll put my fingers in the direction of the electric field, and I'll curl my fingers in the direction of B. And since the x-axis is, you can imagine it pointing out of the board towards you, E, curl my fingers into B, my thumb gives me the direction of propagation of this wave. So fingers in the direction of E, curl your fingers in the direction of B, and your thumb will give you the direction of propagation. Let's try it right here. At this point along the y-axis, E is down, but B is into the page, B is away from us, and so once again, E is down, B is away from us, I get my thumb pointing to the right. So no matter which point I choose, I always get a V that's pointing to the right in this picture. So you can always figure out the relative directions of E, V, and B by using that new right-hand rule, number 4, and you'll certainly get a bunch of practice doing that. A couple of other things. I'll mention that E and B are in phase. All that means is that where E is a maximum, B is a maximum. Where E is 0, B is 0. I already mentioned that, and that's just to say that they are in phase. Now, it turns out that doesn't actually always have to be true. Sometimes it's not true if an electromagnetic wave is propagating through materials. But for the most part, we're going to assume that our electromagnetic wave is propagating through a vacuum. So we're imagining that this is traveling through empty space. In terms of magnitudes, the maximum value of the magnetic field is going to be equal to Emax over C. I'll give you a plausible argument for why that's true, but you can always get the relative values of the electric and magnetic fields by looking at this. Finally, I already mentioned this, but I'll list it again here. The speed of light in a vacuum is equal to 1 over epsilon 0 mu 0, which is lambda times f, right?